In this video, I'm going to present Permutation Index, a method for exploiting data skew to improve query performance in a main memory column store. As an example, consider a large fact table corresponding to the sales of a bookseller. One column of this fact table is the ID of a book, represented as an integer foreign key BID into a dimension table of book information. The query here executes a foreign key join to materialize a column of book prices. To answer this query, the database system can scan the fact table and look up the price column of the book table using BID as an array offset. Because the unit of data transfer between memory and cache is a cache line of typically 64 bytes, even if we want to read just 4 bytes from the price column in memory, the entire line of 64 bytes will be copied into cache. To look up different book IDs, new cache lines will be copied as well. Because of limited cache space, we cannot cache the entire price column when there are a lot of books. If the book IDs are uniformly distributed in the fact table, then many of these foreign key lookups could miss the cache, and they will become very expensive. In real world, however, many data are not uniformly distributed. For example, this figure shows the distribution of book sales in a real dataset. As we can see, about 75% of the book sales concentrate on the most popular half-million titles. With this kind of skew, the query execution is much better because the most frequently accessed data items are likely to be in the cache already. For example, when this highlighted item at BID 81 is very popular, the cache line containing this item will be cached, and subsequent accesses will be faster. However, this cache line contains just a single popular item and 15 other unpopular items. This means that we are wasting 94% of the space to store infrequent data. If we don't carefully control the data layout, popular items will be sparse in the price column like this. To solve this cache utilization problem, we propose an index data structure that we call a permutation index. The permutation index is an array of the same size of a dimension table, and it contains the distinct values of this dimension column in decreasing frequency order. For example, here, record 81 in the dimension table is the most frequent, so 81 is the first element of the permutation index array. Record 27 is the second most frequent, so it is the second element in the permutation index, and so on. An equivalent representation is to use the frequency rank function as shown on the left. Then we can use the permutation index as a reordering template. For the fact table, we replace the foreign key reference to dimension table row I with the frequency rank of I. So, for example, identifier 81 is replaced by the rank of 81, which is 0. This replacement is done when we build the permutation index. Then, to execute a query, we need to pre-process the dimension columns used. So we create a permuted copy according to the permutation index. For example, here, the data item at the original offset 81 is reordered to become the first item which is referenced by the transformed identifier 0 in the fact table. After reordering the data, we have concentrated popular items in a dimension column, and now they are adjacent and share cache lines with other popular items. The diagram on this slide shows the same skewed data as before, but it's after the permutation index transformation. We can see that now a single cache line contains the most frequent items, and the cache utilization becomes much better. We can compare the cache usage between the permutation index and a randomized data layout. This figure shows the access frequency to cache lines during a materialization query on the previous book sales data with Skew. The dashed line here corresponds to the size of the L1 cache. Under a randomized data layout, the popular book titles are sparse, so only about 20% of the accesses hit the cache. With the permutation index, frequent data are concentrated, so the hit rate increases to over 50%. To evaluate the performance under different levels of skew, we implement microbenchmarks under ZIF distribution with varying parameters. We also implemented database operators using AVX file12 instructions. This figure shows the performance of the materialization query. The permutation index approach is much faster than the baseline at around ZIF parameter 1.0. which is actually the common parameter found in many empirical data distributions. For small ZIF values on the left, the data is close to uniform and both methods suffer from cache misses. For larger ZIF values, the skew is very concentrated in a few data items, so both methods have cache hits for most of the time. On the right, we try to use software prefetching to hide the cache miss latency. Both methods become faster, but the permutation index has even better speedup. This figure shows the cache behavior measured by hardware performance counters. We observe that permutation index leads to higher L1 cache hit rates and lower cache miss rates than the baseline. We also see better utilization of the data TLB cache. So at all levels of the cache, the utilization becomes better, and the query runs faster as a result. An important way of using permutation indexes is to use the transformed identifier as an estimation of the value frequency in the table. For example, we know that identifiers smaller than a particular threshold are the most frequent. Then, during query processing, we can just compare with this threshold to separate the code paths of frequent and infrequent data. In this way, we can use faster code for cache resident data, or in parallel execution, we can reduce contention caused by data skew. Here, I will use an example of SIMD aggregation to demonstrate the threshold-based idea. So for a count star query like this, we can use a count array to accumulate the counts for every item. Using SIMD instructions, first we gather current counts from the array. We then update the counts in a SIMD register, and finally scatter the new counts back into the array. However, if there are repeated data in the 16 SIMD lanes, then there's a conflict and we can't just add 1 to the counts. When we have data skew, this problem is more severe because the popular values are more likely to repeat in every 16 items. A general way to resolve this kind of conflicts is to process a subset of distinct values and process the other repeated values in the next iteration. But the overhead of this is quite high, even if we use the AVX512 conflict detection instructions. Because the frequent data are much more likely to cause conflicts, we want to separate the processing of frequent and infrequent data using the threshold-based approach. For the most frequent items, we can replicate the beginning part of the count array for each of the 16 SIMD lanes, so we don't need to resolve conflicts on these most frequent items. Instead, we can just increment the counts for the corresponding SIMD lanes and combine them in the end. In practice, a small threshold works better on a skew, so the replicated arrays have very small footprint in cache. For infrequent data, we still need to do the conflict resolution, but this only happens infrequently. Here are the Microbenchmark results for SIMD aggregation. Comparing the blue and red curves, we can see that permutation indexes perform better than the baseline. However, for both methods, we need to resolve conflicts, and there is a significant overhead at high skew when the parameter is close to 2.0. Using the threshold-based approach, we can solve this conflict resolution problem, and the yellow curve shows the best performance at high skew. In this research, we also tested on several real-world datasets with Skew. This figure shows the results on Wikipedia access data. Using multi-threaded execution, we observe up to 2x speedup for materialization, selection, and aggregation queries. We also see much higher speedup for heavy hitter aggregations. To use permutation indexes in a database system, we need to maintain the frequency information when there are updates. In general, we find permutation index still works under approximate frequency information, so we can simply ignore small updates if they don't change the frequency too much. If there are a lot of disruptive updates and the frequency changes a lot, then the permutation index has to be periodically rebuilt. So, in summary, the permutation index method exploits data distribution to speed up queries. We can improve cache utilization by reordering dimension data, and we find these kind of optimizations work well with SIMD executions. For details on SIMD algorithms, theoretical analysis, and more results, please take a look at our full paper. Thank you for watching.